Okay, welcome to this week's London Learning Lean seminar. Next week, we're going to be hearing from Amelia Livingston, that's me, talking about formalizing algebraic tori. But this week, we're very pleased to welcome Jin from the University of Michigan to tell us about the Erdős-Tuza-Valtr Conjecture. I'm recording the talk, but I'll stop the recording when it's time for questions. Over to you.
Thank you so much for the invitation. So today, I'm going to talk about how I formalized my own result on the Erdős-Tuza-Valtr conjecture. So as we have all seen, there's a lot of drama happening around someone claiming a proof of a notorious conjecture, and there's this whole shenanigan over that on the truthness of the proof. So I thought that was unfortunate, and that motivated to first prove my own result. So today I'm going to talk about what is my main result, and I'm going to talk about its proof and its implementation and the takeaways I had in the formalization. So let me start off with this little theorem called the happy ending problem. To understand this theorem, you only need to know two definitions. First is that a set of points is in general position if there is no 3 point on a single line. So if you actually try to plot a bunch of points on the plane, it is rather an unusual singular event for 3 of them to happen to be lying on a single line. So in this talk, we assume that that case is not happening. And another definition is that if I talk about an n-gon, I'm not talking about any concave n-gon. I'm always talking about a convex n-gon. So a fourgon is a convex fourgon. And with that, the happy ending problem states that any 5 points in general position, there were 3 on a line, contains a convex fourgon as a subset. And what you see in the bottom is a bunch of different cases for that theorem. So for example, if we take all the blue points, 5 points in general position, we have that fourgon, convex fourgon as a subset. And what you see is actually a proof of the happy ending problem. For the proof, imagine that you have a rubber band, and imagine that the points are like nails on the wall, and you wrap all the points around this single rubber band, and it will trap all the nails tightly. And the shape that the rubber band makes is something called a convex hull. So if the convex hull is a convex trigon, what you see on the left is the case for that. You basically draw a large line that passes through the 2 points in the inside the convex hull, and it will not pass one of the edges of the convex whole triangle, and those 4 points form a convex fourgon. And if the convex hull either forms a fourgon or fivegon, you just take any 4 points of them, and it will give us a fourgon. So this is the proof of the so-called happy ending problem. So what you've just seen is a pleasant human proof that any 5 points forces a fourgon. And a similar a theorem happens with 9 points. With 9 points, we force a fivegon, and that has a manageable human proof. But 17 points forcing a sixgon, it doesn't have a human proof. We need some computer to do that. And an analogous one that forces a sevengon, it doesn't have any proof yet, so it's a conjecture. But at least what you see over there is a pattern of numbers. So as we want to have an extra point in the convex n-gon that we want to force, we basically have powers of 2 plus 1, points need to force that. So that is already conjectured by Erdős and Zechers in 1960, decades ago. So if we define large N of n as the minimum value of points that forces on n-gon as a subset, then they conjecture that it's a power of 2 plus 1. And it nearly holds. So asymptotically is kind of solved. So the world records are these. the lower bound, as they suggested this conjecture, they already constructed 2 to the power n minus 2 points with no n gone. So we do know that that number is a lower bound. For the upper bound, however, it was a hard conjecture to lower the base of the upper bound. Before 2016, the best known upper bound had a base of year 4. So it's more of 4 to the power something. Then in 2016, the groundbreaking result of Sook has brought the base from 4 to 2. And then it has been refined further by Holmsen and all the others. So this is a notorious conjecture in discrete geometry. And for this one, oh yeah, maybe I should add this. So this is a type of a Ramsey theoretic problem. And most of the times in Ramsey theory, say if we take the Ramsey number of a graph, we usually don't expect to see any equality. We don't expect to see any of these maximum number to have a formula. But this one does have a conjectured formula. And if it ever is true, that's somehow magical, because a lot of times we don't see equalities at all in those Ramsey theoretic type of problem. So with that, we do have an equality in a little bit of a different setting called cups and caps. So what you see is a picture of a 4 cap on left and a 5 cup on right. So basically a 4 cap is a set of 4 points aligned in the increasing order of x coordinates, so that if you draw them consecutively, it basically forms a concave downwards graph. And similarly for 5 cup as well. And note that n cap and n cup, they are special forms of convex n cup. So with these type of structures, we do know the exact formula for this Ramsey theoretic type problem. So let large n of a comma b be the minimum value of points to force either an a cap or b cup as a subset. Then we have this nice number, which is a binomial, and extra +1 just to make sure that we force such a structure. This is proved by Erdős and Zacharias in 1935. And this actually is quite important. This has been used as a subroutine for both the lower bound and the upper bound for the Erdős-Zacharias conjecture. And now, I get to describe what is the so-called Erdős-Tuza-Valtr conjecture. It's a generalization of both the Erdős-Zacharias conjecture and the Kopskep's theorem. So the idea is simple. Erdős-Zacharias, we force an n-gon. The Kopskep's theorem forces a cap or b cup. So for the ETV conjecture, we just combine all of that. So let large n of n comma a comma b be the minimum value, such that any point set of that number either forces an n-gon, a cap, or b cup. And then they conjectured this number of points to force either one of those structures. And while the summation looks rather complicated, let me note that this is just a consecutive sum of binomials in a row of a Pascal's triangle. N minus 2 is fixed, I spans in a range. And you can see that here we have this little weird linear constraint. I'll describe why, what does it really means very soon. So let me explain why this conjecture specializes to Erdős-Zacharias conjecture and the Kopskep's theorem. So by letting a and b equal to n from the ETV conjecture, we retrieve the Erdős-Zacharias. The reason is this: large n of n comma n, n-gon, n cap, or n cup is just equal to forcing an n-gon, so it's equal to large n of n. forcing an n cap or n cup, it already forces an n-gon. So forcing an n-gon is subsumes like forcing an n cap or n cup. And then the value conjectured by Erdős-Tuza-Valtr matches with the value conjectured by Erdős-Zekers. So it's basically the sum of all the like binomials in the whole row of a Pascal's triangle. So it's a power of 2. It also give us back the Kopskep theorem. For this one, we need to think a little bit more through. So by letting n equals a plus b minus 3, we retrieve the Kopskeps. And the reason is that any n-gon where n is equal to a plus b minus 3, we either have an a cap on top or b cup on bottom. On n-gon, if you imagine, it consists of a big cap and a big cup that meets at both the endpoints. So if you run the lin arithmetic on it, then yeah, it gives us either one of them. So with this, Erdős-Tuza-Valtr, the value conjecture by Erdős-Tuza-Valtr matches with the one suggested by the Kopskep theorem. Okay, so we have seen that Erdős-Tuza-Valtr is a generalization of both. But here's an interesting part. It turns out that the generalization is also implied by the Erdős-Zekers conjecture. So it's supposed to be a generalization, but it is also implied by the original conjecture as well. So they are equivalent, and it is their result, Erdős-Tuza-Valtr, as they suggested the same conjecture. And the reason is this. So basically, if you take any counterexample of the ETV conjecture, you have a set of more than that sum of binomial numbers with no n-gon, a cap, nor b cup. And it turns out that you can add a bunch of points on the left and on the right to make some counterexample of the original Erdős-Zekers conjecture. So with that, not Erdős-Tuza-Valtr implies not Erdős-Zekers, so its contraposition is Erdős-Zekers implying Erdős-Tuza-Valtr. And if you're a fan of computable or decidable math, these statements are all like decidable, finite, so you don't need to worry about that. So yeah, we have just seen that Erdős-Tuza-Valtr is equivalent to Erdős-Zekers. And there's actually something more on top of this going on. So let P of n comma a comma b be the ETV conjecture for that specific parameters n, a, and b. Then actually we have this pyramid of implications. So I think it's worth spending some time going through what this picture means. So each P is an instance of the Erdős-Tuza-Valtr conjecture. On the very top, we have just seen that P of n, comma n, a, b are equal to n. This is equal to Erdős-Zekers conjecture for that specific n. And on the very bottom, what you see is all the instances where n is equal to a plus b minus 3. And we have just seen that these are all Kopskep theorem. So on the very top, we have the notorious Decades-Lowth conjecture. On the very bottom, these are all like classical theorems. And all the statements in the middle, to the best of my knowledge, these are all conjectures. And all these like arrows that goes from top to bottom, they are valid logical implications. So the reasoning is pretty much similar. Basically, if you have a counterexample on the bottom, you can just lift it to top by adding a bunch of points to the left or right. And yeah, I think that describes this pyramid. So it's a pyramid of conjectures with the hardest one on the top. And here is my amazing result. So my result is this one. So I took one step further from the bottom. And my friend told me that I actually did twice of that. By symmetry, if you flip the roles of caps and cups, you also have that as the result. So to reach the notorious Erdős-Zekers conjecture, we only need to prove the remaining cases. I did 2 out of n minus 2 choose 2. So I think you can complete the rest. And thank you for listening to my result. So this is the lean talk. So I should go through its formalization as well, right? So that was my main theorem. Any set of points of that number either forces on 4 cap or on n-gon. I didn't include cup because n cup is already on n-gon. So while it is a very, very small progress towards the Erdős-Tuza-Valtr conjecture, to me, the proof was not so easy. Like, so the Kapskat theorem, you can apply induction on it. But this one, if you try to do direct induction on n, it doesn't work at all. So instead, I figured out that I need to find something called a pair of interweave lace cups. And that thing, I can prove it by induction, and that takes majority of the proof. And also with some non-trivial casework, this so-called pair of interweave lace cups forces on n-gon. And all of this, I'm using some technique called that I named as alpha statistics. Actually, one of my professors did. But anyways, and this alpha statistics thing is based on the amazing work of Moshikovitz and Shapira. And with all that, I managed to prove this special case of ETV. So this is the whole like proof structure. Main lemma, if you have a bunch of points, then you find a pair of interweave laced cups. And then from that interweave laced cups, I force on the n-gon. And this is formalized. So on the top, you see the statement, you have a bunch of points, it forces an n cap or an n-gon. And on below, I basically find something laced. And I use that this laced implies n-gon, so that completes the proof, like I described just before. So why did I really do this? This for me was because the proof was too confusing for me. Like it had a lot of technical definitions, lemmas, and without lots of generalities. It's not that like it's too complicated in terms of philosophy. It just had a lot of alphabets and like things going around in the proof. And even like I wanted to make the proof simpler. So with my professor, we worked hard to make the proof simpler. But even after doing that, like the main proof was rather complicated. So like these all come from the one single proof. So like I had 1 star and 2 star, and 2 star is some weird like assumption implying 4 different things. And I used that in the middle to imply 5 different things in the other paragraph. So yeah, I didn't think that it was rather pleasant to have that. So I wanted to make it simpler. And I also had the like not like a doubt, but like I was worried if worried about the possibility that the whole proof could be wrong, because I might have missed one of the conditions, maybe. So at least with formalization, now I'm quite confident that it's true. So the formalization is done. And I think this is more important. So after formalizing all of that, with like 2 months of just programming with no production of new theorems, I think I did have some takeaways. So while this could be something basic to lean experts, I learned that proof verification is a kind of software engineering. So the Curry-Howard isomorphism basically says that a proof is a kind of a program. Proof of A implies B is just a function that takes a proof of A and returns a proof of B. So writing proofs in this lean is some kind of like a programming. So we need to have some kind of like care, and like there's some kind of craftsmanship and art going behind it. It's not that I'm good at it, like I learned that there's some like this happening with formalization. So I especially have like these three takeaways as I formalized my own result. First is a time-consuming task, writing a lot of trivial codes. So I want to first go through that. And with this, it will be also an opportunity for me to talk about like how it's implemented. So for implementation, so it's about, the result is about a bunch of points on the plane, right? But I actually didn't use real numbers at all. Instead, what I used is a generalized combinatorial model of convexity. So what I defined was something called configuration, and it is a finite abstract set S of points equipped with these. First, I want an ordering of those points, and this is supposed to model the ordering of points by its x coordinates. And next is an assignment, abstract assignment of whether like 3 points in the increasing order x, y, z either forms a 3 cap or a 3 cup. So with this, I'm able to model like all these different types of convexity structure of like points on the plane. So if you do have actual points on a plane, then we do have a corresponding configuration. Basically, you order the points by its increasing x coordinate and just assign whether they form a 3 cap or 3 cup by actually how it is in the plane. But like with this abstract setting, most of the configurations, you can just arbitrarily assign like each triple, whether they form a 3 cap or 3 cup. And these are not realizable by actual points at all. But still, like my proof like works with this setting. So this is a setting that I like went with. So this is the definition of a configuration. So we do have what is a linear order. So alpha is the type of points, and we supply a linear ordering on that. And then I abstractly assign whether 3 points form a 3 cup. And this is just to make sure that we can decide whether those 3 points form a cup or a cap. And also, let me note that I think experts will be familiar with this technique. But here, I don't force the like 3 values for this cup3 function to be increasing in the ordering. Instead, I just ignore like whatever it gives for any x, y, and z not satisfying the required condition. This makes the programming easier, and it doesn't hurt any like trueness of the formalization. The reason is because you don't need to carry around the proof of y greater than x all the way around. Okay, so with this, the definition of cups, caps, and gons extend naturally. So this is the definition of a cup for a general configuration. So a list is an n cup if its size is n, and the points in L appear in the increasing order of like the configuration. And finally, and most importantly, maybe any 3 consecutive points in this list form a 3 cup in this configuration. So you can see that if this configuration C really comes from actual points, then it does form the cup that we just described before. And it turns out that the last one actually needed quite a bit of work to like make it work. So we needed a notion to say that any 3 consecutive members of a list satisfies some property, which is they form a 3 cup. So on the top, what you see is an example of a chain prime in MATLAB. So there is a vocabulary in MATLAB that says that like in a list, any 2 consecutive like things satisfy some condition. But what I needed was a like 3-valued version of that. So I need to say something about 3 consecutive members of a list. And this one, like chain, which is something I named as chain 3 prime, is not in mathlib. And it turns out that I had to write like a bunch of like codes only for this chain 3 prime, a bunch of lemmas, and which is simple or which is simp lemma or non-simp lemma, to make to make it workable to like prove other things. So I had to kind of duplicate a small portion of like mathlib for chain 3 prime. So here's an example. If P and Q are like cups and A, B, C are points, so that P ends with A, Q starts with C, and if PAB, ABC, and BCQ forms a cup, then we can actually join all of these cups to make a big cup. So this is necessary to combine like all these different cups. And normally we wouldn't like write this as a theorem because it's rather obvious once we imagine about it. But I had to prove this in the formalization process. So while it would have been a waste of paper to write that, but we need to prove that as a simple lemma to work. So yeah, with this, I learned that like we need to implement a lot of that things happening in our brain, like as a single step. Like sometimes we need to write a lot of code to like fill that out. And it's pretty much the same with programming. Like it's easy to imagine that you click a button and it should work, but to actually do that, we need to write a lot of like a boilerplate codes to make it work. But still, like programming, proper API designs and refactoring helped me a lot. So I wouldn't say that I did a superior job at like designing it great, but I think the point is that trying to do so helped me a lot. So here is an example of that. So like object-oriented programming, if you have a new concept, designing a good interface on it really helps. So here is an example where I take a large cup and I take both endpoints. And not only that, like you will have a smaller cup in the middle, right? And that's supposed to give us a cup as well. So this is a small lemma that takes both endpoints and like also gives a proof that the middle one is also a cup. And another lemma is this. This one, I take a n cup and I try to take some portion of it from right. So if m is some number that is smaller than n, then I can take an m cup by taking m points on the right. And it's going to not only give us an n cup, its right endpoints is the same as the one we had in the beginning. So like all these like manipulations with cups, it happens almost quickly in our brain, but these all need proof and formalization. And by properly naming that and like thinking through like the list of what I need for the proof and properly naming that helped me a lot to translate my thought process as is like into codes. So API design helps a lot. And also refactoring helps a lot. And I think this is an interesting experience. So this task of formalization is time consuming, and it really forces you to make the proof as simple and modular as possible. So after doing that, I have to get rid of one definition and 2 technical lemmas in my proof. And the weird artifacts that you have seen in the main proof, they are factored out. And I'm going to like write that, I like take that into account in my new version of the draft. And I do feel like I have a much clearer picture of why it really works. And with all that, like the programming was much easier because the logical steps and context you need to carry, these are much smaller. Like each piece are smaller, so it's easy to program. So yeah, I think I learned this. And finally, I think I want to talk about design choices. So in programming design, people say that design choices are important. I've experienced the same thing in my formalization project. So we just seen a definition of a cup and a cap using configuration. When I initially started this project, I brought this up in the Zena Discord, and people told me that I should use this definition instead, maybe. So here, what you see is an alternative definition of a cup. So this R basically is cup 3, like whether they form a like 3 cup or not. And then we have a global list of points S. So not only this S is a list of all the points, it's ordered already in the increasing order X coordinates. And if you define cup L in S this way, it's a valid definition. So any 3 consecutive points, they form a 3 cup, and all the points appear as a subsequence of S. So it means that the points appear in the increasing order, and they are all in S as well. So with this one single line, it does all of that. But then as I went through this definition, I found this. So in the proof, a lot of like operation like this is happening. If I have a cup PXQ and another cup XYQ, then it's rather obvious that we can join them to have a bigger cup in the same global set S, right? So I needed to prove that. But with this definition that we have just seen before, that thing is not true. So it seems like it matches with the definition PXY and XYQ are cup. But here, the problem is that we don't force, we allow duplicated members in the global list of S. So with this particular like a counterexample, this example is not true. So this can be saved by saying that in our global set S, global list S, we don't have a duplicated member. So S dot no duplications. With this is true. This is true, but it needs extra work to locate the cups PXY and XYQ in the same position. Like we do know that RXY and XYQ, they like lie as a subsequence of like S, but how do we know that those X and Y, like from RXY and XYQ, lie in the same position? And that's rather non-trivial work to prove. So yeah, with this, it's still workable, but I eventually resorted to the configuration definition of those 2 reasons. So first, I wanted to say that Y is on the right side of X, Y is greater than X, and use trichotomy a lot without depending on any global set. And the second is that I felt like the concern that a list is a cap and is in some set S, those are 2 different things. And I thought that the alternative definition had those 2 combined. So I thought it would be better to have them separated. So this is what I came up with. So the join PXYQ forms a cup in my definition. And the proof here, note that there's no dependency on a global list S. So there's no mention of S. And also whether they form a cup is just really about using chain prime and chain 3 prime. So just a bunch of simple lemmas deals with that all. And another concern that I separated is that the join should be in the set S. And for that, I devised a local notation for that. A list and a fin set, these are 2 different things. So you can just use the subset notation So I devised a notation that a list is inside some fin set like this. And with this and a bunch of list.in simp lemmas, this thing is just killed by simp. So at least for me, it was much easier to like modularize the code and progress. But still, to be honest, I still don't know if it was the best choice. It also had drawbacks and consequences as well. Like, yeah, it's hard to describe it for this moment, but I think what's more important is that like we have those two worlds diverging like in the beginning of the project. And if you take one of them, like the codes that you will see and like the way how you think through in formalization, it will be drastically different than the other options. So we need to be aware of like our design choices and make our like choices deliberately, even though we may or may not make the right one at the beginning. So that was my like final takeaway. And this is a summary of what I learned. And this time, really, thank you for listening. So yeah, this ends my talk. And if you have any questions, feel free to ask me.